So, moving on, we will talk about some common theorems in vector calculus. Okay. So, before we come to theorems, we again have to get familiar with the different kinds of integrals that are there. Okay. We have so far looked at partial derivatives, we have looked at dot product, we looked at cross product. So, those are differential elements. The next thing important component is the integrals. So, as you can imagine, there are three kinds of integrals that we will look at. So, there are line integrals, surface integrals and volume integrals. So, the line integral over here is as before, there are two kinds. I can go from point A to point B, like we had done that before, right. So, that is one point over here, one point over here, my A and B, okay. So, depending on the nature of A, this integral may or may not depend on the path taken. We have seen that if A can be written as grad f, then this integral does not depend on the path. Okay. So, this is one kind of integral. The other kind of line integral is also something which we have seen, which is a integral around a closed path, right, and the notation for that is, okay, we can put usually a path that is denoted by some symbol. So, for example, this is a path and I denote it by gamma, capital gamma. So, these are the two kinds of integrals that we will come across, okay, pretty simple. Then comes surface integrals. Okay. Now, how many kinds of surfaces do you expect? Very simply, open and closed surfaces, right. So, for example, if I take a cup over here or a saucer over here. So, the surface of the cup represents a open surface, right. So, let us call this S. So, this integral can be of this form, okay. Similarly, if I now close this lid over here, right. So, it is a cup with a lid on top of it. Now, it is a closed surface and then that same integral is represented with the same symbol over here and I write it as, okay. So, an open surface, I cannot talk about how much volume it encloses, right. So, I cannot say, so the volume is either you can say infinite or you can say undefined. But a closed surface encloses a certain finite amount of volume. So, that is important to remember. And finally, the other kind of integral that we come across is a volume integral. There is not much different over here, it is just integration over a closed volume V. Sometimes you might encounter an expression like this, it is an integral of a vector over the volume. We should not get afraid, all we have to do is open up the component. So, this is going to be integration along each component, dV remains the same, Az dV, okay. So, this quantity finally is going to be a scalar or a vector? It is going to be a vector, right, and the components of the vector are given by these amounts over here. Those are the components of this vector, okay. One small thing that you will have to get used to is regardless of the dimensionality of the problem, for example, this is a 1D, this is 2D and this is 3D, we are only going to put one integral sign, okay. In other courses you may have seen that if it is a two dimensional integration you will be putting a double integral and you will be putting a triple integral, but we find that from the context it is clear whether it is a single integral, double or triple integral because of the differential element, okay. So, if you see a dx, dy, dz, you know it is a volume integral. So, we will not be putting these multiple symbols over here, it will be clear from the context, okay. Alright. So, just one thing to keep in mind, here you can in the one dimensional integral over here, this dl you can see is a small line element with some length and direction. In the case of the surface, how does the surface element look? It will be having something like this, right. It is a small patch with a normal vector, right. So, it has some direction and it has some area, okay. So, this ds over here that I have written, you can write it like this, mod ds, which is the area and the vector over here, okay. So, that is implicit and understood when we write ds vector. For volume integrals we need not worry, there is no direction, it is just the take a differential volume like this, and that is the volume inside, dx dy dz. So far I have been using the language of x, y, z, but it is not necessary. I can use the spherical coordinates r theta phi or use cylindrical coordinates rho z phi. It depends on the problem at hand. We use the convention depending on what makes it easy to solve that problem. So, these are the integrals that we will come across. Okay. Let us move to our first main theorem in vector calculus, which is most commonly known as the divergence theorem. Different books will refer to them as by different names. We have also studied the same theorem by Gauss's theorem, or in electrostatics called Gauss's law. It is also called Green's theorem. Okay. Both Gauss and Green are names of famous very old scientists. Okay. So, to explain this, let us first write a intuitive sort of give an intuitive geometrical interpretation of what this divergence theorem is. And the simplest way to think about it is, let us say that I have a tap, okay, and which is giving out water over here, and let us enclose it in some imaginary volume over here. Okay. So, it is a closed surface, that is what we are doing. And I want to find out how much, I want to do a balance of the water inside this, this diagram that I have drawn. So, right now there is only one tap over here, and let us imagine I am considering this in steady state. Okay. Steady state, that means the tap has been on for a long time, whatever water had to fill up in this volume has filled up, right. So, if I wanted to measure, let us say, the water outflow from this surface, so this is a surface S enclosing a volume V. Okay. So, water is going to be going out from this surface, obviously, because the tap is here. Okay. It is a magical tap, it has no connection, it is just there, it just appeared. Okay. So, there is water that is going out from here. So, what could you do? You could just stand on the surface over here and just measure how much is the flux, right. Flux is how much is going out. Now, if water were, for example, in this surface over here, if water were flowing like this along the surface, it would obviously not flow out. So, there is a flux that depends on the orientation of the surface. So, there is a normal vector over here and the vector how much it is going out from here, right. So, if you look at the expression of the theorem that I have written over here, this expression over here is outward flux. Okay. Remember, the ds had the normal vector inside it over here, as it made sense, and I had to take the dot product of the vector field with that normal vector, that gave me how much was going out. Okay. So, this makes sense for counting the water going out. I can do a more direct calculation. If I know the tap, if I know how many taps are in this, right now I have shown only one tap, but there could be more taps, right. So, I have taps. What was the expression or quantity which I had described, which measured how much outgoing a vector field was? It was the divergence, right. It told me how much something was going out. So, I take this vector field A, which is representing water flow. If I find out its divergence at various points inside this, I will get a sum total of how much is outgoing, right, but that is at each point in the volume. So, that is the expression over here. This is the how much it diverges, and I have to do this integration over the volume because there could be lots and lots of taps, right. So, these are two ways of counting the same problem, and that is the geometrical intuition of how do we calculate this, how do we do the budgeting of the water. You could either do it over a volume V, or you could do it over S, and remember that this surface has to be closed because I am talking about a volume, right. So, hence this closed surface over here. So, this is your divergence theorem. Okay. This was the geometrical intuition of it. We will come to the proof sketch shortly. One comment I want to make over here, how many dimensions is the left hand side being? How many in the integral is in how many dimensions? In 3 dimensions, it's a volume integral, whereas the right hand side is an integral in how many dimensions? 2 dimensions, right. So, from a computational point of view, this is the point I want to make, that it helps to reduce the dimensionality of a problem. Let us say that there is a problem that I am solving by the left hand side, then to numerically solve it, I have to break up the volume into small pieces and do some calculation over each part of the volume. Whereas the right hand side is telling me that the same calculation can be done only on the surface, I need not go in, right. So, we know that the volume is a larger quantity than surface, right. So, this helps us, this is a trick which we use to reduce the cost of computation, okay. This is again a very computational idea of the divergence theorem. Now, the proof sketch for this is fairly simple. So, I will not outline it fully, but we will just have a brief idea of it. Let us start with the right hand side. Okay. So, the right hand side is telling me it is the flux of A from some surface. So, let us take a small box. So, this is my x, y and z is pointing upwards over here. This is my small box. Okay. And let us say that the center point over here is x naught, y naught, z naught, and in each dimension I have the width of this box delta x, delta y, and vertically over here is delta z. Okay. Now, for this very small volume V, let me try to calculate the right hand side. Okay. So, the right hand side, now for this surface, for example, let us take the surfaces this one and this one. Okay. So, these are surfaces for which what is the outward normal for this surface, right. So, for this surface it is x hat, and for this surface the normal is pointing in the backward direction, right. So, it is going to be minus x. So, this is minus x. Okay. So, let us just do the calculation of the surface integral over here. Let us just take the x surfaces, x hat surfaces. Okay. So, let us assume that this volume is very small such that this function does not vary very much inside it. So, if I take let us take this side first over here. So, what can I call it? So, it will be we can assume that the value of the function is more or less constant. So, I can call this a of which component of a is going to come? It is going to, I am taking a dot product with the normal, right. So, the normal is along x hat. So, which component of a will survive? Only x. Okay. So, I will write this as a x. Okay. What are on this surface over here, what are the values of the coordinates? Right. So, I will have x naught plus delta x by 2, right. What about the second coordinate? The center of the box is y naught z naught, right. So, what I am doing is I am trying to find out the value of the function at the center of this face. Center of this face is simply going to be y naught z naught, okay, and minus the contribution from this side. Okay. From this side the contribution, again which component survives? X is what survives, that is right. What is the value, what is the argument over here? X naught, exactly. So, it is the back side. So, it is away from the center by a distance of minus delta x by 2. The other coordinates remain the same. Okay. So, this is the vector component coming from A, and I need the only thing missing is now what? The surface area. So, what is the surface area of this? Right, not dy but delta y and delta z, right. Okay. Now, does this remind you of something, this expression over here? A very tempting thing to do is to multiply and divide by delta x, right. So, if I do that, right, so I will get delta x, delta y, delta z, and this thing over here, right, x naught plus delta x by 2. I am going to leave the other components the same because they do not change, right. This is going to be x naught minus delta x by 2, do not change, and the whole thing divided by delta x. And if I take the limit as these guys tend to 0, this expression will become, so this over here, what does this become? dV, right, this becomes the differential volume, right, and this expression over here, notice which is the component that is changing in this, only the x component, right. So, it is dAx only by dx, right. So, this is considering the surfaces with normal x hat. Similarly, there will be two surfaces with normals y hat, two surfaces with z hat, right. So, I have got what will happen is common will be dV, then I will have a partial with this other terms will give me this, and finally the, right. So, that is how we get it, and this looks exactly like our expression over here, right. So, we have a satisfactory geometrical idea over here which talks about volume flowing out, and we can prove it in a very simple way, and hopefully this has given you enough confidence on how to solve this. Okay. So, this is the divergence theorem, and as I mentioned that it helps us to reduce the dimensionality of the problem. Let us move to the next object which we have considered, which will be involving the curl, right. So, that is the curl theorem, also known as the Stokes theorem, right. So, Stokes theorem is going to relate the curl to something over here. So, this is the statement of the theorem. As before, we will take a geometric picture of it and then look at how to prove it. Okay. So, the geometric intuition of the curl itself was how much it swirls, right. So, now that is the curl of A over here. So, it is telling me how much a vector field swirls, but that is not all. There is a dot product with a surface vector, a differential surface element. So, it is the swirl of a vector field, and after that the flux of that, and then an integral. Okay. So, note that this is what kind of an integral is this, a closed or an open surface? It is an open surface, right, it is not, the circle is not around it. So, I can think of a surface like this, and in this, so this is my surface S over here, write it over here. So, let us take one small patch ds over here, this ds has some normal vector over here, right. Now, in this surface patch over here, what is happening is I am calculating the outgoing flux of the swirl, okay, and it is to be done over the whole surface. So, I will have to break up this surface like this into various patches and sum it up. Now, remember we are talking about the swirl of a vector, right. So, this in this patch how much it is swirling, in this patch how much it is swirling, and so on. Now, you can see if I take, let us take a zoom in of this interface over here, right. So, I have two patches that are side by side, right. This patch over here, the swirl is going in this direction, in this patch the swirl is going in this direction. So, if I look at this common edge over here, these swirls are in some sense cancelling off. So, what will I be left with if I sum it up over this, if I sum it up over all of these patches, what are the parts that will not cancel? The outermost edges, right. So, whatever is happening over here, that is not going to cancel, right. So, geometrically what we can say is, okay, you want to calculate the outgoing flux of the swirl, very good. Instead of doing it over every element over here, why not just walk along the surface over here and collect the vector field that is along the surface, that will give me the swirl, that is my A dot dl. So, A dot dl around the surface boundary gamma is what I can get from here. So, okay, so geometric picture is very clear. There are swirls over here, they all cancel at the internal boundaries, the only place they do not cancel. So, look at this, let us zoom in over here, let us look at this swirl over here. So, over here it is going in this direction, no one to cancel it, similarly here, similarly here. So, may as well just directly take A dot dl over here, sum it up over the curved surface, and that is our geometric picture of the Stokes theorem, right. If you did not know this, you might look at this expression and feel very scared, what so many ugly looking quantities, but the geometric picture is very clear. Similarly, now for this expression, what can we do? Let us try to sketch out the proof like we did previously, okay. So, again we will take the right hand side, and to make matters simple, we will just restrict ourselves to a patch in the xy plane. So, this is my xy, this is my patch, okay. Center point again I am going to take x naught, y naught, and this patch has some delta y and some delta x is the width of this patch, and this is how I am going to sum up this, evaluate the right hand side over here. So, this is what I am going to do, A dot dl. Okay. Now, my vector field, that the way I have drawn it, let us just assume that A is is in the plane. So, Ax, Ay and 0, that is my vector field. Now, I want to, so let us start from here, okay, and go in this direction. So, let us assume that this delta x and delta y are very small quantities. So, I can approximate this part of the integral simply by the value of the function at this point multiplied by the length, okay. Because we are assuming Ax and Ay do not change so much, it is a very small element. Anyway, we are going to take the limit delta x, delta y going to 0, right. So, when I do this, I am going to write it as, so let us write it over here, sorry, this is what I am going to write. The first term, what will I get? Ax dot dl. So, for this path, what is dl along, so let us call it path 1, 2, 3 and 4. Along path 1, what is my A dot dl? So, delta x is the element, right. So, I am going to write delta x is the length element, that is along which component of A will contribute to it? Ax, right. So, it is going to be Ax. What are the coordinates I should put down for this function? At what am I evaluating it? So, x naught and y naught minus delta y by 2. Remember, the center is x naught, y naught. So, this point is x naught and less by delta y by 2, right, that is the distance over here. So, this is this thing. Now, so let us go back to this, okay. Next, so this is from path 1, let us write down the contribution from, next instead of writing from path 2, let me write from path 3, let us just change the order, it does not matter. So, from path 3, what will be the contribution? Which way is dl? Minus, right. So, it is along minus x hat direction. So, I am going to write a minus, the length element is again going to be delta x, and which component contributes? Ax or Ay? Ax again is going to contribute, and what do I have over here? X naught and y naught plus delta y by 2, okay. So, this was for path 1 and path 3, okay. Now, let us go back to the remaining two paths, which are path 2 and path 4. So, for path 2, what is the differential element? Delta y. What component of A is along this path? Ax or Ay? Ay is going to be my component, Ay. What are the coordinates? X naught plus delta x by 2 and y naught, and when I go along path 4, my dl is pointing in the minus y hat direction, right. So, this is going to be minus delta y, Ay x naught minus delta x by 2 y naught, okay. So, in other words, what I did was I took path 1 plus path 3 plus path 2 plus path 4, that is the order in which I did it, okay. Okay, so, now let us look at these terms 1 and 3 together. What is common is delta x, and in paths in 2 and 4 delta y. So, like we did previously, our trick will be to multiply divide by the missing one. So, in the first two terms, what I can do is multiply and divide by delta y, right. So, this will become delta x, delta y common, right, and what I have is so Ax, x naught, y naught minus delta y by 2 minus Ax, x naught, y naught plus delta y by 2, whole thing divided by delta, what did we divide by? Y, okay. And the other term that I will get is delta, so delta x, delta y, Ay, x naught plus delta x by 2, y naught minus A y x naught minus delta x by 2 y naught, whole thing divided by delta x. So, as before we will take the limit that delta x delta y they tend to 0. So, this is the limit. So, then this expression delta x into delta y will become ds, right, ds. What happens to the first term over here? This is the, it is a partial derivative, it looks like a partial derivative of which component? Ax with respect to y, but with a negative sign, right. So, this becomes minus dAx by dy, and the second term is the partial derivative of the y component. So, with a plus sign, right, and that is, if you work out the curl expression over here, this is which component of curl, right. So, there is x and y, what is missing is z. So, this is actually the z component over here, right. So, this is the starting with a geometric idea which gave us the statement of the theorem very intuitively. The proof is again not very difficult, we just looked at a surface and the line that is around the surface and we did a simple integration, right. So, this gave us the z component. If you had a general surface oriented along with normals in each component, you will get all 3 components. Okay. So, again very straightforward using the simple intuition about integrals and flux. So, this tells us about the Stokes theorem. Now, moving on, there is one small variation of the Stokes theorem which we will talk about. So, the Stokes theorem as before, but in what is called a multiply connected region. Okay. So, previously we had our surface over here was whole, right, I mean homogeneous, there were no holes in it, right, and the integral was around the bounding surface gamma. Now, in a multiply connected region, what we will have is, let us say a surface like this, but let us say there is a hole in it. Okay. That hole does not exist. For example, maybe it's there are no electromagnetic fields there, or let us say it's a room and inside a room there is a Faraday cage. Inside the Faraday cage we know that the field is 0. So, why try to calculate it? So, we will exclude that area or volume from the computation by means of a hole, right. So, this is the hole. Okay. So, now this surface S over here is bounded by 2 lines or contours, right. So, one is this one. So, we can call this gamma 1 and here is another line which or contour which bounds it, gamma 2. Okay. And we want to know what is the Stokes theorem saying for such a volume, for such a surface over here, right. Now, as you can see, the statement of the theorem shows you the difference between 2 line integrals. Earlier we had only one line integral, now we have 2 line integrals, gamma 1 and gamma 2. And what is the intuitive explanation for this? It's again the same as the geometric picture that we had, that there are many swirls over here, right. So, if I take this over here, this swirl over here did not cancel off from anywhere else. Similarly, when I take this surface element over here, I am going to have the part along here is not going to cancel from anywhere, right. So, if I call this, let us call this dl1 and let us call this part over here dl2. Okay. So, dl1 is pointing in this direction and dl2 is pointing in the opposite direction. Okay. So, when I do this the budgeting over here, del cross A over the whole thing, what will happen is that the first component will come from dl1, right, and the direction is the same as the direction over here that I have shown of gamma 1, right. So, it is in gamma 1 is in this direction. So, this term is fine. Why is there a minus sign over here? You can notice that for this surface element, the part that did not cancel out was actually flowing in this direction. But if I take a convention that I am going to always give a orientation for my contours in, let us say, a counterclockwise way, right. So, gamma 1 here is counterclockwise, gamma 2 is shown in a counterclockwise way. Then this contribution here is appearing in a clockwise sense. So, that is why I have to put a minus sign over here. Okay. So, this is the second term. So, again this convention may not be universal, some books may have different orientation or sense of orientation. So, when I write it in this way, it is implicit that gamma 1 and gamma 2 follow the same convention, which is counter clockwise. Okay. And then you can extend this idea to multiply connected regions. Okay. So, let us say I have a volume like this, multiple things that are being cancelled off over here. So, I have overall let us say gamma, and I will call this gamma 1, gamma 2, gamma dot 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 gamma n. So, what will happen is that I just have to subtract off the line integrals along each of these things, right. So, if I have say n such holes over here, this is hole 1, hole 2, hole 3, I mean sorry, this is hole n, I am going to have how many summations, how many integrals on the right hand side? So, 1 from gamma and then minus a summation gamma I closed and I is equal to 1 to n. So, I have a total of n plus 1 integrals on the right hand side. Again, yeah. The directions of, yeah, oh, that is a good point, right. So, the direction is should be in the counterclockwise way, right. So, it should not be this, it should be this thing, alright, thanks for the correction, okay. So, all are counterclockwise, okay. So, as I sort of motivated this to begin with, this is helping us reduce the domain of computation, right. If I know that there is something which is of not interest, which is not of interest to me, why should I calculate it? So, I can remove these elements from the integration. Small price I have to pay is, okay, a few more line integrals have to be evaluated, okay, and now the surface is excluding this. That is the meaning of S over here. Okay, so this is Stokes theorem in a multiply connected region, which we will use in the course. And so